Hello there, Mr. Sutton here, bringing you the Algebra 2 Honors 7-4 Part 2 homework solutions on adding and subtracting rational functions. In this one specifically, we are graphing things by first breaking them down with a little inspection and also taking a look at complex fractions. On this problem, they want us to first rewrite the g function in that transformation form and then graph it. So in order to do that, we've got lots of tools. We're going to use inspection on this one though. So I basically want to rewrite my numerator so that there's an x minus 1 up there that I can cancel. Now in order to make that happen, if I had a 5x minus 5, then I could factor out a 5 and have an x minus 1. In order to get a minus 5 up here, I have to split up this negative 7. So what plus negative 5 would give me negative 7? Negative 2, I think, right? So if I split this up into negative 5 minus 2, that's what the 7's turning into. Then I can factor a 5 out of those first two terms. That'll leave me with x minus 1 inside. And while I do that, I'm also going to move this negative 2 off into its own fraction with its own denominator of x minus 1. Now I can cancel out these x minus 1's over here. And just kind of rewriting this, I've got negative 2 over x minus 1 plus this 5 right here. So that's the form that they were looking for. Now to actually graph this thing, let's take a look at the transformations that are happening. So this negative 2 in the numerator, that's giving me a vertical stretch and a vertical reflection. The x minus 1 down here translates me 1 to the right, and the plus 5 out here is translating me up 5. So summing all that up, vertical stretch and reflection, translation right 1 and up 5. So here's my parent table. We have negative 1, and 1, 1 for these rational functions. And my modified table now, for the x's, we're just going right 1. That's the only horizontal change. So x plus 1 for that. For the y values, we've got a few things happening. We have a negative 2 times all the y values, and then we have to add 5 to those. So negative 2y plus 5. Doing my x plus 1 first here, negative 1 plus 1 is 0. 1 plus 1 is 2. And then for the y values, negative 2 times negative 1 is positive 2, plus 5 gives me 7. Negative 2 times 1 is negative 2, plus 5 is 3. And since I shifted 1 to the right, my vertical asymptote is going to now be x equals 1. And since I shifted 5 up, now I have y equals 5 for the horizontal asymptote. So putting that all on a graph, and I'm making my grid lines high enough here so that I can accommodate these values. We've got our vertical asymptote at x equals 1, horizontal at y equals 5, and now I also have the point 0, 7 right here, and 2, 3, which is over here. So here's my upper left branch and my lower right branch, and that's it. For this problem, I'm trying to first rewrite this in transformation form and then graph it. So the method we'll use on this is inspection. In order to get this started, I'm asking myself basically, what do I have to split this constant up here into so that when I factor out this 6, I end up with an x plus 5 that'll cancel. So if I want to have something, 6x plus something that would give me x plus 5 when I take out a 6, well, 6x plus 30, 6 times 5, that would work. So I need to split this 4 up into 30 plus something else. Well, what would I have to add to 30 in order to get 4? How about negative 26? So if I rewrite this as follows here, I can take a 6 out of my first two terms. That'll give me my x plus 5 that I wanted to cancel with that denominator. And this 26 I'll move into its own fraction with its own x plus 5. So plus negative 26 over x plus 5. X plus 5's are canceling. And now I can rewrite this as negative 26 over x plus 5 plus this 6 in the beginning here. I just switched the order. And that's the form that they were looking for. So now what does this actually look like in terms of transformations? Well, this negative 26 up here is giving us a big vertical stretch and also a vertical reflection. The plus 5 down here gives us a left translation of 5, and the plus 6 out here is shifting us up 6. So we've got a vertical stretch and reflection, translation left 5 and up 6. Here is my parent table. We had -1, -1, and 1, 1. And for my G table now, I'm going to have, for the x's, I'm shifting actually left 5, so I'm going to have to do x minus 5. And then for the y values, the stretch and reflection, we have to multiply -26 times the y values, and then we have to add 6. So -26y plus 6. All right, let's apply these now to the few points here. So -1 minus 5 is -6. 1 minus 5 is -4. And then applying the y rules here, -26 times -1 is +26. Plus 6 gives us 32. -26 times 1 is -26. Plus 6 is -20. And my new vertical and horizontal asymptotes, for the vertical, since I shifted left 5, I now have x equals -5 for that one. And for the horizontal, since I went up 6, now I have y equals +6. All right, let's put it all on a graph. I've made my grid lines go by 2's on the x-axis so I can get this negative stuff here. And also I'm going by, looks like 8's on the y-axis so that I can get all the way up to 32 and then a little bit more. So my vertical asymptote, we have -5, that's going to be right here. And for the horizontal, y equals 6, that's roughly here, 3/4 of a grid line up. We have the point -6, 32, which is right there, and -4, 20, which is about halfway between -16 and -24. So here is one branch up there, and the other branch down here. For this problem, I'm trying to take this general linear form and rewrite it as a transformation. So this one's a little bit tricky to do by inspection, but I'll show you how we could do this. So basically, I want to get an x minus 5 in the numerator after I factor a 12 out of whatever expression is up here. Because that would allow me to cancel out this x minus 5. So what would I have to add to 12 that would give me a 5 when I take a 12 out of here? Let me think. Well, 12 times 5 is 60. So if this were 12x minus 60, then that would do the job. Now, what would I have to add to -60 to get, well, there's nothing here, so 0. Oh, how about +60? So if I rewrite the invisible 0 up here as -60 plus 60, that doesn't change the value of anything, but it gives me this -60 to play with. So taking a 12x out of these first two terms now, that leaves me with x minus 5 inside, which was what I was aiming for. And then this 60 here gets its own fraction with the x minus 5 as a denominator. So these x minus 5's cancel, as I planned. And now we have 60 over x minus 5 plus 12. So for transformations, the 60 up here gives us a vertical stretch. The x minus 5 gives us a translation of 5 to the right. And the plus 12 gives us up 12 for that translation. So vertical stretch and then right 5 and up 12. Here is my parent table with -1, -1, and 1, 1. For the g function, since I'm going right 5, I need to do x plus 5 for that rule. And for the y rule, since I'm stretching by 60 and then going up 12, I need to do 60y plus 12. All right, let's apply these rules now. So we're adding 5 to the x values. -1 plus 5 is 4. 1 plus 5 is 6. And then we've got, for the y rules, 60 times -1 is going to be -60. Plus 12 is -48. And then we have 60 times 1, which is 60, plus 12 is 72. The new vertical asymptote, since I shifted 5 to the right, is now going to be x equals 5. And for my horizontal asymptote, we went up 12 on our translation, so we're doing y equals 12 for that one. So for my grid lines here, my intervals, I'm going to make my horizontal ones go by 2's. And for the vertical, I mean, -48 to 72 is quite a range there, so I'm going to make these go by 24's so that I can fit everything I need to. So for my vertical asymptote, we have x equals 5, that's right over here. And then y equals 12 is the horizontal, which is half a grid line this way. Next we have the point 4 comma negative 48. So over 4 down 48. That works out pretty well. And we also have 6 comma 72, which is right here. That's on a grid line. So that worked out fantastic going by 24s. So we have this branch down here in the lower left and this branch in the upper right, and that's it for this one. To simplify this complex fraction, we're going to first find the LCD of all the subfractions here. So we only have two real denominators that aren't just ones, 3 and x. So our LCD then just needs a 3 and an x in it. Now I'm going to multiply all of these by my 3x LCD, all the numerators. And 10 and 6, by the way, count as numerators because there's an invisible divided by 1 for each of those. So we have 3x times x, 3x times the 6 here, times the 10, and times the 4 up here. Now let me cancel out what I can. I can cancel out these 3's up here and these x's down here, and that's actually about it. So let me see what's left over now that I've done that. In my numerator, x times x gives me x squared. And we have negative 6 times 3x, so that's negative 18x. In the denominator, I have 3x times 10, so 30x. And these x's are canceled, so I just have 4 times 3, which is 12. Now, it is possible to factor each of these. The numerator, I could take out an x, leaving me with an x minus 18, but none of that's going to cancel anything down here. And if I took, I guess I could take a 6 out here and get 5x plus 2, but again, that's not going to cancel anything that's up here. So I'm just going to leave this the way it is. There is one little extra piece that I need to throw in there, however. Since I did cancel out these x's on the way here, I need to say x does not equal 0, because 0 initially would make the original undefined, but it doesn't mess up the simplified one, so this is a whole truth in advertising sort of thing. To start simplifying this complex fraction, I need to find the LCD of all the subfractions in here. And to do that, it would be helpful if I factored this top right fraction a little bit. So for that one, I can take out a 4, it looks like. That leaves me with 2x minus 5. And since that matches all these other ones, that turns out to have been a very helpful thing to do. So for my LCD, I need a 4 and a 2x minus 5. And that actually covers everything. So that works out really well. So let me multiply all my numerators by my LCD now. So you get a 4, 2x minus 5, and you get 1 up here, and this x gets another 1 as well. So I can cancel out the 2x minus 5's in the top left. In the top right, I can actually cancel out the entire LCD in denominator, so that's fantastic. Down here, I can cancel out 2x minus 5's. Let's see what's left. So up here, we just have a 4 times a 1. And we have a minus 7, so that actually worked out very simply. And then down here we just have 4x. Just simplifying the numerator a little bit, that's going to be a negative 3 over 4x. Can't really do anything else there. What I do need to do, however, since I canceled out these 2x minus 5's, that means I have to basically set that not equal to 0 and leave out that x value so that it's not... people can't plug in something that would make the original undefined. So if I set this piece equal to 0 and solve it, I have to add 5 and divide by 2. So we see that x cannot equal 5 halves. Again, that would make the original undefined, which we don't want.